Welcome back, everyone, for another deep dive. This time, we're looking at something pretty wild that happened during the Artemis I mission.
Yeah, definitely a little unnerving.
So picture this, you have the Orion spacecraft. It's coming back from the moon, right? It's getting ready to hit the Earth's atmosphere. And that's when things get a little dicey with the heat shield.
Yeah, for sure. And, this is a big deal because without the heat shield, well, let's just say things would get very toasty.
Exactly. It's what keeps the spacecraft from basically disintegrating. So you can imagine why everyone was on edge when they noticed a problem.
Especially since we're planning on having astronauts on board for Artemis II.
Right. That's the whole point, right? To get humans back on the moon and beyond. So what exactly went wrong? Did the heat shield just fall apart? Was there like a giant hole in it?
Well, not exactly. It's a little more complicated than that. The problem was with the material that the heat shield is made of. It's called Avcoat.
Avcoat.
Ah.
Sounds pretty high tech.
Oh, it is. It's this incredible material that's designed to burn away in a controlled way during reentry. It basically sacrifices itself to protect the spacecraft.
Oh, that makes sense. So the heat shield is supposed to burn, but then what was the issue?
The issue was that it didn't burn away as smoothly as expected. It started to crack and shed unevenly.
Doesn't sound good.
Not ideal, no.
Yep.
And during the investigation, they found out that gases were getting trapped inside the Avcoat.
Oh, so like pressure was building up.
Exactly. And that pressure led to the cracks.
Interesting. So why weren't these gases escaping? Was there something blocking them?
Well, you see, Artemis, I used a special re-entry technique called skip guidance.
Skip guidance.
Yeah, basically the spacecraft dips in and out of the atmosphere, kind of like a stone skipping across a pond.
Oh, I see. To slow down gradually.
Right. And this skip guidance, well, it actually resulted in lower heating rates than they initially planned for.
So the heat shield wasn't getting as hot as it normally would.
Exactly. And that's where the problem lies. The lower heating rates, combined with some of the Avcoat's properties at those temperatures, it meant the gases couldn't vent properly.
So it's kind of like trying to blow air through a really thick piece of fabric.
Yeah, that's a good analogy. It's much harder than blowing air through something more porous.
Got it. So skip guidance, lower heating rates, trapped gases, cracks. I'm starting to connect the dots here.
Yeah, you got it. Now, the big question is, what does this mean for future missions?
Especially since we're talking about putting humans on board.
Right. And that's what's so fascinating about this whole situation. It really highlights the challenges of space exploration and how even the smallest details can have a huge impact.
Absolutely. And we'll dive more into those challenges and what NASA's doing to address them right after this. All right, so we're back and ready to dig deeper into how NASA is tackling this heat shield puzzle.
Yeah, definitely a puzzle. And, the stakes are pretty high.
Absolutely, especially with Artemis II right around the corner. So are they scrapping skip guidance altogether? I mean, it seems like that would be the easiest solution, right?
Well, not so fast. Remember, skip guidance has some major advantages. Like you said, it helps to slow down the spacecraft gradually, but it also provides more flexibility when it comes to the landing site.
Oh, right. I remember you mentioning that. So what are they doing? Are they just going to cross their fingers and hope for the best?
Oh, no. They're way more proactive than that. NASA is taking a multi-pronged approach, you could say.
Multi-pronged. What does that mean?
Well, for one thing, they're looking at ways to improve the Avcoat material itself. Making sure those gases can vent properly, even at lower heating rates.
So they're basically redesigning it.
In a way, yeah. They're using all the data they gathered from Artemis I to create a new and improved version of Avcoat, one that's more porous, you could say.
More porous, so it's like poking tiny holes in it to let the gases escape.
You got it. Well, not literally poking holes, but you get the idea. But it's not just about the material itself. They're also looking at the manufacturing process.
Oh, so like how they're actually making the Avcoat.
Exactly. Remember all those samples they took from the Artemis I heat shield? Hundreds of them.
Yeah, you mentioned they were analyzing them under a microscope. But what were they looking for exactly?
Any inconsistencies, any imperfections, anything that might have contributed to those cracks forming. They wanted to make sure that every single batch of Avcoat is consistent and reliable.
That's incredible, the level of detail they go in.
Oh, yeah. It's all about precision in space exploration. Every little detail matters. And this whole investigation has already led to some pretty significant changes.
Really? Like what?
Well, for example, they've identified certain manufacturing techniques that can help create a more uniform Avcoat material.
Well, it's like finding the perfect recipe, right? The right ingredients, the right process.
Exactly. And all of this is designed to make the Avcoat more robust and less prone to cracking. But of course, all this testing and refining it must take a lot of time and resources, right?
That's what I was thinking. I mean, how do they even test these new heat shield materials?
Well, that's where those high-tech facilities come in. The arc jet chambers and the wind tunnels.
Ah, yes, the ones that simulate the fiery reentry. That sounds pretty intense.
Oh, it is. Imagine an oven that can reach temperatures hotter than the surface of the sun. That's an arc jet chamber. They use it to test how the heat shield materials hold up under those extreme conditions.
Wow. And what about those wind tunnels? What do they do?
Wind tunnels simulate the aerodynamic forces a spacecraft experiences during reentry. Basically, they create these powerful gusts of air that can reach supersonic speeds.
So they're testing for both heat and wind resistance.
Yeah.
That's pretty thorough.
Yeah, it has to be. They run multiple simulations, tweaking different variables to make sure the heat shield can handle any scenario they throw at it.
So it's not just about making the Avcoat more porous, it's about making it more adaptable as well.
Exactly. They need a heat shield that can handle a variety of conditions, not just the ideal ones.
I guess when you're dealing with space travel, there's no room for error.
You said it. And all this testing and development, it's expensive. But when you consider the stakes involved, it's an investment worth making.
For sure. I mean, we're talking about human lives here.
Yeah.
But, all this talk about Avcoat makes me wonder, is this going to be the standard heat shield material from now on?
Well, that's a good question. And it really highlights how space exploration is a constantly evolving field.
So there's no one-size-fits-all solution?
Not really. Each mission has unique requirements. The type of spacecraft, the reentry speed, the trajectory, all of these factors play a role.
So what works for Artemis II might not work for a mission to Mars, for example.
Exactly. A Mars mission would require a completely different set of heat shield characteristics, maybe even a completely new material.
Wow, that's mind-blowing. It really shows just how complex space exploration really is.
Definitely. And this whole heat shield situation, it just goes to show that we're always learning, always pushing the boundaries of what's possible. And that's what makes it so exciting.
It's like a constant cycle of challenge and innovation, right?
You got it. We face a problem, we find a solution, and then we face a new problem, and so on.
So it's not just about reaching a destination. It's about the journey itself. The problems we solve, the things we learn along the way.
Exactly. And who knows what incredible discoveries await us in the future.
It's really an incredible time to be following space exploration. So much is happening. So while NASA's busy perfecting the Avcoat for Artemis II, what broader lessons can we take away from this whole heat shield saga? What does it tell us about the future of space travel?
That's a fantastic question, and one that I think deserves some deeper thought. We'll be right back to explore those broader implications right after this.
Okay, so we're back, and I'm really curious to hear your thoughts on what this whole heat shield situation, what it tells us about the bigger picture of space exploration, where we're headed and the challenges we might face.
Yeah. I mean, it's definitely a good reminder that space travel, it's not easy.
It's not a walk in the park, right?
Right. Even with all the technology and planning, things can and do go wrong. And those things, they can have a domino effect. You know what I mean?
Absolutely. Like with the Avcoat, right?
Yeah.
Something seemingly small, like gas permeability, it can turn into this major headache.
Exactly. And I think that's one of the biggest lessons we can take away from this. We have to be adaptable.
Adaptable.
Yeah, we can't just design for the ideal scenario. We need systems that can handle all sorts of curveballs,
Like a spacecraft that can roll with the punches.
Yeah, basically. Like with the skip guidance and the heat shield, it highlighted how important it is to have a thermal protection system that can perform well under different conditions.
Different heating rates, different atmospheric conditions.
Right, it's got to be flexible, it's got to be robust.
So it's like having a plan B, C, and D all ready to go just in case.
Pretty much.
Yeah.
And then, of course, there's the importance of testing.
Yeah, you can't just wing it in space.
Not if you want to come back safely. I mean, look at the investigation NASA launched after Artemis I. Super thorough, analyzing every little detail.
All those samples, all those tests, all that data?
It all adds up. It helps us understand what happened, why it happened, and how to prevent it from happening again. It's how we learn and improve.
So it's like a continuous cycle. We encounter a problem, we investigate it, we find a solution, and that solution might lead to new challenges and so on.
Exactly. And this cycle, it's going to be even more important as we set our sights on more ambitious missions, like sending humans to Mars.
Yeah, I just thinking about that. Mars, it's a whole different ballgame, right?
It is a much longer journey, a much higher reentry speed, a whole different set of hazards to think about.
So the Avcoat, even the improved version, it might not cut it for a Mars mission.
Probably not. We'll likely need to develop completely new thermal protection systems, new materials, new designs that can withstand those extreme conditions.
So like what kind of crazy stuff are they cooking up?
Well, there's a lot of research going on right now. Some folks are looking into inflatable heat shields.
Inflatable? How does that even work?
I know, right? It sounds wild, but basically they'd inflate during re-entry, creating this big puffy shield. And then there are other teams experimenting with these advanced ablative composites.
So like a super strong heat-resistant material.
Yeah, exactly. Stuff that can really take the heat. But it's not just about the materials themselves. It's about how they're integrated into the spacecraft design, Everything has to work together perfectly.
Yeah, it's like one giant complex puzzle where every piece is critical.
You got it. And you know what I find most inspiring about all of this? It's this constant drive to innovate. We're not satisfied with the status quo. We're always looking for ways to improve, to push the limits of what's possible.
And that's what makes space exploration so fascinating.
Yeah.
Right? It's this incredible blend of science, engineering, human ingenuity.
Exactly. It's about exploration. It's about discovery. It's about pushing the boundaries of human knowledge.
And it's not just about the destination. It's about the journey itself, the lessons we learn along the way, the challenges we overcome.
Well said. And who knows what amazing things we'll discover next.
That's the beauty of it, right? It's this vast unknown just waiting to be explored. Well, a huge thanks to you for walking us through all of this. This has been an incredible deep dive into the world of Orion's heat shield and what it means for the future of space travel.
Thanks for having me. It's always a pleasure to talk about this stuff.
And to everyone listening out there, keep looking up, keep exploring, and we'll catch you on the next deep dive.